Okay, there are several ways to prove that the medians intersect in the given ratio. I'm going to go for a geometrical proof here, or at least the outline of a geometrical proof, but I'll mention a couple of other things that we could have done. So to start with, all I've done is I have extended the line, or produced the line BQ, as you can see here, and I've now constructed another line coming from the vertex C that's parallel to the line AP, as you can see. I'm going to look at the triangle I've now highlighted in yellow and the smaller one that I've highlighted in green. And what you should be able to see is that those two triangles are similar. Why? Well, they share a common vertex, which is the vertex QBC. And then if you think about the angles between parallel lines, it should be fairly clear that the other two sets of angles are also going to be congruent to each other. So they're similar triangles, and furthermore, because P is the midpoint of the segment BC, we can also see that the scale factor of the enlargement is in fact a scale factor of 2. Make sure you're happy with that. If you're not, then let me know and I'll do it in a slightly more formal fashion. Okay, we're now going to move our motivation across here, and we're going to note that angle PAC is congruent to this other angle that I've shown here. Why? Well, they're Z angles, given that these were parallel lines. I'm also going to note that these two angles are congruent because they're vertically opposite angles. And again, we note that Q is the midpoint of the line segment AC, and so I'm going to make the claim that they are also congruent to each other, as shown. And what we now have is the ASA theorem, which demonstrates that we have two congruent triangles. Now, just let me try and highlight those without making a mess of this. So we're basically saying that this triangle then is congruent to this triangle here by the ASA theorem. Okay, so what I can now say is that these two sides then are congruent to each other. And if you remember what we said earlier, that the green triangle was similar to the yellow triangle, but and there was an enlargement factor of 2, then we should be able to see that this length over here, let me put another letter on, hang on, where are we up to? We've used a Q, let's call that, I don't know, T perhaps, T. Then we can see that TC, we call that one in the middle an M. TC is twice as long as MP, and we've just shown in fact that TC is the same as AM. So in other words, AM is twice as long as MP, and hence we will have the ratio as desired. Alternative ways of solving this problem. What you could do is give coordinates, general coordinates, to the points A, B and C. I think I'd probably let B be at the origin, that will make life easier, and then say that A is at the point x1, y1 and C is at the point x2, y2. That would allow us to quite easily find the midpoint of these lines just by taking the average of the end points, and then we could, for example, intersect, finally just solve simultaneously the intersection, say, between AP and BQ, and that would work out quite nicely, I think, especially, as I say, if you make B at the origin. Another possibility would be to use vectors, actually. So if we define some vectors, perhaps BC is equal to A and BA is equal to B, and we've got the midpoints as shown, I think we could probably find a couple of different journeys, say a journey for PM and a journey for PA, and that would also give the given ratio. Kind of similar to a GCSE problem, but obviously one where no information is given, and probably a little bit trickier actually. And there is a final way that I've seen this one done before actually, which was done involving finding various areas of the triangle and the sort of proportions of the areas that you would have. I've never tried that on myself though. Okay, well I hope there's something within that which will allow you to come up with a proof. If there are any more questions about this one, then obviously just send a message.